This video is on regression analysis and specifically how to use regression analysis to evaluate the quality of a cost driver. Is the cost driver a good cost driver? Does it have a relationship with the costs that we are trying to predict? Remember, in the high-low method, we were able to look at a scatter graph and get an idea of whether a cost driver had a relationship with the costs or not. But for a more rigorous or analytical way to do that, we would use regression analysis. Now, before there were computers, people did regression analysis by hand, but it is time-consuming and tedious, so we're going to use Excel for that. The data is in Excel. Week 1 through 10 is the same as we used in the high-low example, and the costs are the same as we used in the high-low example. I took the cost driver that we used in the Excel example, and I have called that machine hours. It's in column B, labeled MH. And one manager thinks that machine hours are driving the costs, and another manager said, no, I think it's direct labor hours. And so we have gathered direct labor hours for weeks 1 through 10, and we'd like to do 2 regression analyses and compare the results and see which one is the better cost driver. We will use the results from that analysis to write the y equals VX+F equation so that we can make point predictions, and we'll take a look at a point prediction. To start regression analysis, you want to come to the Data tab, and all the way over to the right, there should be Data Analysis. Now, this is not automatically loaded into Excel when you start the program because not everybody does data analysis. So if it's not there, if you go to the Data tab up here and there's no data analysis over here, then come back to the File tab, come down to Options. When you get to Options, go to Add-ins, and you want to go to Manage Excel Add-ins down here at the bottom. And make sure that Analysis Toolpack and Analysis Toolpack VBA are both checked, and hit OK. And then it should be up here under Data, all the way to the right, Data Analysis. If it's not, try closing Excel and opening it again and seeing if it's there at that point. So we're going to click on Data Analysis, and this has a variety of tools in it, all statistical tools. We're going to choose regression, so click on regression and hit OK. And then it's going to ask us to input our ranges. So the first one it asks us to input is our Y range. Let's go back and look at that again. Input Y range. Click on the little red arrow. And remember that the Y is our dependent variable. It's the variable that we are trying to predict, or our cost. It's the number on the Y-axis. So we're going to select our costs and then click OK there. And now it asks us for the X range. The X range is the independent variable. It's the number that we're trying to use as our cost driver. Let's select machine hours and see how we do. Notice that I have selected in both cases the title as well as the numbers. So I want to go in and make sure that labels is clicked. We can tell it to put this into a new worksheet ply, or we can tell it to put it into an output range right on the same sheet, but let's go ahead and do a new worksheet ply. And we're going to just click OK. And notice that it came up here on a new worksheet ply. And I'm going to rename this worksheet Machine Hours. And I'm going to clean this up a little bit. I just made this wider so that we can read this. These first 3 numbers are actually percentages. And then I'm going to take all the rest of these numbers and just put them into comma format. So now let's just take a look at some of the things on this screen. The first thing that we're interested in is the R-square. The R-square is also called the coefficient of determination. And this tells us what percentage of the variance in our dependent variable is explained by our independent variable. In other words, how much of the cost we're trying to predict is explained by or driven by machine hours, and in this case 86%, and that is really good. 86% is an excellent R-square. Another thing that we want to look at is the standard error. This standard error is $95.17. That is basically telling us that when we make a prediction, it may be off by as much as about $95. That's not too bad. If you look at most of our costs, they are about $680 up to about $1,450. So that's about 10%. We can look at the T-stat. Generally, a T-stat above about 3 is pretty good. The bigger the better. Notice that for the intercept, that is our fixed cost, the T-stat is 4.66, and for machine hours the T-stat is 7.03. So that means those are both indicators that this is very good. Another number we want to look at is the p-value. P stands for probability. The probability value, or p-value, is the probability that we got these results strictly by chance. Now, they look like they are 0.00, but there's always a possibility that this is strictly by chance. So let's look at the p-value for machine hours. You can see that it is actually a 0.000109, etc. chance. So a very small chance, about 1/100th of 1% chance that this is all just random. That's a pretty good p-value. That's an excellent p-value. Usually we talk about p-values that are at the 1% level, the 5% level, or the 10% level. Okay, so let's write the equation. Remember that equation is y equals Vx plus F. Y is the cost that we're trying to predict. V is the variable portion times the number of cost drivers. In this case, our cost drivers are machine hours, and then F is the fixed portion, which is also the intercept of the graph. So when we're looking at our regression results, we're still trying to predict Y. Our variable costs are $14.22 per machine hour. That is our independent variable, and the coefficient of that independent variable is the variable cost per unit. Our fixed costs are the intercept, so 424.62. So there is our equation for predicting costs now, using machine hours as the cost driver. So what's the lower and upper 95% stuff all about? Well, this is telling us that there is some possibility that these coefficients are not completely accurate, but there is a 95% probability that the intercept, for example, the true value of the intercept falls somewhere between $214.44 and $634.79. You don't need to worry too much about that, but you can see that the range there is a couple of $100 on either side of the true value. The same thing for the machine hours. The true value, there's a 95% probability that the true value, the true variable cost, is somewhere between $9.50 and just under $19. They're predicting that it's $14.22, but somewhere in that range. We predicted in the high-low video, we were predicting what would happen if there were 45 machine hours. So let's take a look at this. We have $14.22 times 45 machine hours, and our fixed cost, of course, is $424.62. And so the total cost when machine hours equals 45 is the sum of these two. So our predicted value is $1,064.52. Let's go back to sheet 1, which has our data on it, and we want to see if the other manager is got something with this direct labor hours. So let's do the regression again. We're going to come up to data, data analysis, regression, okay, Our y range, that's our dependent variable, or what we're trying to predict. Our x range, in this case, is going to be direct labor hours. And we chose our labels, so we have labels checked. We're going to say new worksheet ply. We're going to hit OK. And we're going to clean this up again. What are you seeing already as we're looking at this? Do you see any numbers that you can evaluate? What do you think about the fit of this direct labor hours equation? Well, let's start out with our R square. Our R square is saying that direct labor hours only explains about 13% of the costs that we've incurred. So this is not very good. And the standard error is very large. You can go down and you can look at the t-stat. Neither t-stat is over 3. So those are not very good. The intercepts p-value looks like it is okay, only about a 6% probability, but that is random. But the direct labor hours, 30% probability that it is strictly random. When you're looking at that lower and upper 95%, the other thing that you notice here is that we have a negative number and a positive number. They don't even know for sure, or the analysis isn't sure, whether the coefficient sign is positive or negative. So this is a really poor fit. I'm not even going to do the equation or a point prediction on it. We can go back with very good comfort and tell the managers that no, in fact, we want to use machine hours. The machine hours, we have 86% coefficient of determination. We have t-stats that are good and strong. We have very low p-values. Our range, our 95% probability value is really good and strong. Okay, the last thing I want to do is go back to the first sheet, and I want to do the regression one more time and show you a couple of the other options that are available on that regression tab. So let's go to data, data analysis, regression, okay. We can check our y range is D3 through 13. Our x range is B3 through 13, which is what we want. We've got labels checked since we chose the labels at the top of the data. You never want to check constant as 0 because that forces the intercept to be 0. In other words, it forces this to be a strictly variable equation. If you knew that you had a strictly variable cost, you wouldn't need regression analysis to analyze it. I'm going to go ahead and I'm going to put the output range so that we have the actual data next to it. And I'm going to check line fit plots just to show you what that plot is. And you can play with these other ones later if you'd like to, but the line fit plots is kind of interesting. I hit OK. Here's our regression. This is exactly what we had before, but let's look at the residual output for a moment. This is telling us that for observation 1, if we use the formula that we came up with, then we would have gotten 1220.98. Our actual cost, you can see, is 1,090, and so there is a residual. There is a difference there. It's not a big difference. It's about 10%. And you can go down and you can look at all of these different residuals. The last one is very close, right? It predicts 737, and we actually have 730, so it's only $7 off. This is also shown on this plot here. Let's kind of make this plot a little bit bigger and look at it. This is showing the orange squares are the predicted costs. So you notice that that is a nice line. The predicted costs are going to be linear because this is a linear regression analysis. It's forcing everything onto the line of best fit. If you look at the blue dots, those are the actual costs. And so we can see how far the actual costs are away from their predicted cost. We can look at one that's further away here. Let's look at this one. So this is the predicted cost is 837 and the actual cost was 680. So that is our 29 and 680 data. If we come down here, week number 5, observation number 5. So this one is pretty far away. But this gives you an idea of the goodness of fit as well. Let's go back to our regression results and do a real quick overall review. The R-squared, the coefficient of determination, that tells us how much of the dependent variable is explained by the independent variable, or how much of our costs for the month are explained by machine hours, how good of a cost driver that is. We want to look at the t-stat, the larger the better. We want to look at those for each row of the regression. The p-value, the probability that these happened only by chance, that these results are strictly random. And in this case, it's the best p-value you can get. It's a 0.00. We want to look at our range, our lower and our upper 95%, and make sure that those look reasonable, that they're not negative and positive, that they're not all over the board or so incredibly far apart that it's meaningless results. When we have that, we can take our coefficients and we can use those to write our equation. And once we have the equation, we can use that equation to make a point prediction like we did here for machine hours at 45. That is the end of the regression video.